Now we'll be moving on to chapter 3, which is all about the very important topics of momentum and energy. The first thing we want to look at is momentum, and there's a quantity that is very related to momentum called impulse. And so these are the first two definitions that we're going to have in this chapter. And momentum is defined simply as an object's mass times its velocity. That's it, mass times velocity. Mathematically, momentum is very often represented by the letter P, which is an odd letter choice, but that's just what's commonly used. And so we can say that the formula for momentum is that the momentum P is equal to m times v, where of course m stands for the mass and v stands for the velocity. Now, since velocity is a vector, that means momentum is a vector. In other words, what does that mean? It means the direction matters, right? The direction of momentum matters. But the definition is mass times velocity. Now, there's something related to momentum called impulse. An impulse is defined as the average force applied to an object times the time over which that force is acting. And so the force times the time gives you the impulse. So here is the equation that relates the impulse to momentum. How are they related to one another? This equation tells you. Now, the basic idea is that impulse is what creates a change in momentum, or impulse changes momentum. And so the relationship is that F average delta t, and of course you'll remember that's the impulse, that is related to the change in momentum. And so this guy here is the momentum, and we know that mass times velocity is momentum, so that's what that is. And of course, you might remember that this triangle here is actually not a triangle, it's the Greek letter delta, and it means change in. And so here we see a delta there and a delta there. So this is F average delta t, that means the force times the change in time, is equal to the change in m times v, which is the momentum. The impulse equals the change in momentum. That is the relationship. Now, if we look at the figure over here, figure 3.2 from your textbook, it gives you an example of this. And it says, when you push with the same force for twice the time, so you've got the same force, but you've doubled the time, that means you're going to double the change in momentum. In other words, you impart twice the impulse and you produce twice the change in momentum. Okay, in this slide, we are looking at this relationship still. The impulse equals the change in momentum. Now we have a couple of different situations. We have this truck here, which is moving, so it's got some momentum, m times v, and it's being brought to a stop. So something's applying a force to it to bring it to a stop. So in the top picture, it's a bale of hay. So the truck runs into the hay, and the hay slows the truck down until the truck stops. In the other case, the truck runs into a wall. Now, the difference between being stopped by a bale of hay and being stopped by a wall is the amount of time it takes to stop. And so the bale of hay is going to slow the truck down gradually. And so this is denoted here. You can see the impulse is F times t. F is little and t is really big. The amount of momentum you have is mv, and then the final momentum is 0 because v is equal to 0 when you stop. So the change in momentum is just going to be mv minus 0, which is mv. That's your change in momentum, and that, whatever that number is when you calculate it, that's equal to F average delta t. If the time is very big, that means the force is going to be really small. This is our basic idea. Now, when the truck hits the wall, the time of impact is much smaller. The wall brings the truck to a stop much more quickly, and so the time is very small, but that means the force in order to stop the truck has to be correspondingly large. That's why slamming into a wall is much harder to recover from than slamming into a bale of hay. The bale of hay will slow you down slowly, the wall will slow you down very fast, and in order to do that, the wall has to apply a much bigger force to the truck, and so the truck gets smashed up.
Boxers also make use of this principle. If you're getting punched in the face, you want to roll with the punch. In other words, when the punch makes contact with your face, you want to move your head, move your body back, and roll with the punch. You want to extend the time of contact. You want to make the time that the punch is in contact with your face, delivering momentum to your face, you want to make that time as long as possible. Because if the time is big, the F will be small. Whereas if you just lock your face rigidly and, lock your neck and you just take the punch, well, the punch is going to be delivered to your face much more quickly because you're not rolling back with it. You're just like your face is like the wall and the punch is being stopped very quickly. So the time is very small. That means the force that your face absorbs is much bigger. That's why rolling with punches is a better way to be hit. You just, preferably wouldn't be hit at all, but if you're going to be punched, you want to roll with it. And that's why it's a physics principle. Now, airbags in your car work exactly the same way. If you are thrown forward in your car and your face hits in the steering wheel of your car, that steering wheel is going to stop your face really quickly, and that means that it's going to apply a huge force to your face and your face is going to be smashed. Whereas if the airbag inflates and your face hits it, the airbag is more like a pillow. It's going to extend the amount of time that it takes your face to come to a stop. And so that means the force delivered to your face is going to be correspondingly lowered. Now, it's a little bit of a fib to say that an airbag is like a pillow. It's actually a metallic mesh bag. And if you've ever been hit by one, they hurt like the dickens. They can break your nose, they can break your fingers, but, it's still much better than taking the full-on steering wheel dead stop. And it's this principle of momentum equaling the change of impulse that is at play. So let's see if we can apply this idea to another principle, bouncing. And so here's a question. What would be better, for a flower pot to fall on your head and stop, or to fall on your head and bounce upward? So here's case one. We have this flower pot, and this is your head, this is the flower pot. The flower pot falls down and it lands on your head and it smashes into your head. That's not going to feel too good. But is that better or worse than having that flower pot bounce upward? In order to answer this, we have to make some assumptions. And one assumption is that it's going to take roughly the same amount of time either way. So we're all hard-headed here. So the flower pot's either going to come here and hit us and stop, or it's going to come here and hit us and bounce back up. Here's why it's worse if it bounces. If it falls to your head and stops, the change in momentum is just 1 mv. So it had mv, and then you brought it to a stop, and so that's 1 mv's worth of change. But if it bounces and it goes upward, your head has to deliver an additional mv's worth of impulse to change its momentum and make it go upward. And so the change in momentum is bigger with bouncing. And so if the time it takes for the bounce is the same as the time it takes for it to stop, it requires much more force to bounce than it does to come to a dead stop. Now this is an old-timey example, but it's still a nice example of this principle in action. This is a water wheel, and so you can imagine that there is some water that is falling into these buckets, causing this wheel to turn. And that could be used to generate electricity or to mill some grain or whatever you're using your water wheel for. But originally, water wheels had kind of flat pans. And what would happen was the water would fall in them and kind of stop. And Pelton was this guy who came up with this design where the buckets where the water is caught have this sort of curvature to them and this shape so that the water, when it falls on them, it's directed to bounce out. And what that does is that creates a bouncing effect where you get more momentum change, and that gives you a greater force to turn the wheel. So let's look at a quick example here. We have an 8-kilogram ball is rolling at 2 meters per second, and it bumps into a padded guardrail and stops. The question is, what is the momentum of the ball just before it hits the guardrail? Well, that's pretty easy. We know that the momentum is equal to the mass times the velocity. In this case, that's going to be 8 kilograms times 2 meters per second. And that gives us 16 kilograms times meters per second. And that is our answer for part A. Now, part B says how much impulse acts on the ball. Now, we have to recognize that the ball's moving at 2 meters per second, and then it comes to a stop. So what's its final momentum if it's stopped? Its final momentum is 0. The change in momentum is going to be 16 kilograms meters per second minus 0 kilograms meters per second. And so that's how much impulse has to apply to affect that change in momentum. In other words, we know that the impulse, which is F average delta t, that's equal to the change in momentum, which in this case is just that same 16 kilogram meters per second. Now, the next question is how much impulse acts on the guardrail. And that answer would also be 16 kilogram meters per second. This is kind of like Newton's third law. The force is going to be equal and opposite. But that fact that it's opposite tells us that the impulse has to be negative. Because like momentum, impulse is also a vector. The direction matters. And so this is sort of the basic idea. Here's another example that we can look at. This time we're not calculating the impulse, we're actually going to calculate the force. And so the question says, an ostrich egg of mass 1.0 kilograms is thrown with a speed of 2, that should be 2 meters per second there. I left off the units. I apologize about that. That should be meters over seconds right there. And anyway, it's caught in a sagging bedsheet and brought to rest in 2 seconds. The question is, what average force acts on the egg? And so we know F average delta t is equal to the change in momentum. And what does it mean when we say change in momentum? It means the final momentum, mv final, minus the initial momentum, mv initial. So F average, and I'm going to drop the average and just call it F delta t. We know it means F average. That's going to be equal to the final momentum, which is 0. And then that's going to be minus the initial momentum, which is 1.0 kilograms times 2.0 meters per second. And that's just 2.0 kilogram meters per second. And so that should all be in line, kilograms meters per second. I ran out of room there. But that is the momentum change. And what must that equal? That must equal F delta t. So F times delta t is equal to 2.0 kilogram meters per second. And what's delta t? Delta t, we're told, is 2 seconds. And so F times 2.0 seconds is equal to 2.0 kilogram meters per second. If we divide both sides by 2, that gives us 2 divided by 2 gives us 1, and the F works out to be 1.0. Now, the units are weird. It's kilogram meters per second and then divided by seconds. That's MA, right? Kilograms is mass, acceleration is meters per second squared, and so we know that the force unit is properly going to be 1 Newton. And that's our answer.